Hi everyone, good morning to all. And we will start our class in some time. Let's wait for others to join, okay?
Okay, sir.
Okay. Okay, so we'll start our class now. And so today we are going to see thrust and pressure. Till now we have finished till gravitation. After this, we'll be doing work, power, energy, and the last chapter, waves. Okay. So I'll share my screen. Please let me know if you are able to see this. Can you see the screen?
Yes, sir.
Okay. So see thrust and pressure. To understand this, first let's we need to ask few questions to ourselves, like why the boat do not sink in ocean, right? You have seen boats floating on water, or maybe a paper boat that you make all the time. Why do they not sink in water? And maybe you'll observe that after some time the boat will sink. It's like the paper boat that you make, right? Or why a needle sink in some liquid, or let's say water itself? Or why do oil, have you seen oil floating on the surface of water, right? You have seen that. So let's say if you have a beaker or some vessel you have, okay? So if you have some vessel, and you, let's say you added, first you add oil, okay? First you are adding oil to the vessel, and let's say the oil is occupying this place. Now what you do, so this is oil. Now what you're doing, you are adding water, okay? Now you are adding water. So initially the water will be here, but you'll see gradually the water will start coming downward, and this oil will start going in the upper layer. Okay, so how it will look like after some time? Okay, let's say this is T is equal to 0, and after some time in the beaker, what you'll see that water has settled at the bottom, and in the top surface you have oil. Okay, so oil will be here, and this will be water. Okay, see, first you are pouring oil, then you are pouring water, but ultimately oil will always float on water. What's the reason behind this? Okay, we need to understand that part. All right, or why milk after boiling? Let's say, have you ever boiled a milk, or have you ever seen milk boiling? What will happen after, if you keep supplying heat to the milk, you will see that the milk is coming out of the vessel, right? It will start coming out of the vessel. So what are the reasons behind it? Okay, so the reason is again thrust, pressure, and density. Okay, there will be a new term that we'll be learning in this chapter, that is called density of the material. Hopefully you guys might have heard this before, but let's do it again here itself. Okay, so thrust. Can anyone tell me what thrust is? Yes, anyone? How many of you are present here? Let's see. Okay, are you guys listening?
Yes,
Ashwini and Niket. Okay, I think someone's stapler is there with me, a blue stapler. Whose stapler is that? I took it by mistake. Please ask your classmates whose stapler. Maybe next time when I'm visiting the school, I'll return it back. Okay, and I'm really sorry about that. So you guys can hear me, right? So 5 of you are here, but okay. So thrust, can you tell me what a thrust is? Thrust is a force. It's a type of force. Okay, type of force. Like we have studied thrust, sorry, we have studied forces like contact and non-contact forces, right? We have also seen 4 fundamental forces. Thrust is also a type of force, like centripetal force, right? That always acts towards the center of the revolving object. Okay, and similarly, thrust is a force which always acts perpendicular to the body. Suppose a block is kept on the desk. Again, I'm taking that same classic example. So there will be weight acting on this block of this, the mass, because of the mass of this block, and there will be upward force, right? So upward normal force, normal reaction force will be acting on this. So here, this normal force is called thrust. Okay, this normal force here is called thrust. It may not have to be always in the upward direction. It can be in any direction. Okay, but it will always act perpendicular to the body. Always act at right angle, perpendicular to the body. Okay, and let's take another example. Let me make an aircraft, or let's say kind of aircraft. I don't know exactly how to make it. It's not a dolphin, by the way. If you guys are about to say that, so please don't do it. So this is your rudder, elevator, and the wing, of course. So let's say that's our aircraft. Okay, so if this is our aircraft, and see, aircraft is having some weight, right? So the weight will be acting in the downward direction towards the center of Earth, right? Weight of aircraft, which is mass of aircraft into acceleration due to gravity. And to balance, since the aircraft is moving upward, right? Aircraft has to fly. So it cannot have a force just in the downward direction. It will have an upward force, which is called lift. Okay, lift force. Okay. All are forces. Weight is also a force. Lift is also a type of force. Then see, because there are air everywhere, right? And the aircraft is moving in the air, right? In the air it is moving, and because of this air only, the aircraft is able to produce lift with the help of its wings. Okay, so because of this air, there will be a force acting in the opposite direction of the aircraft. That is called drag. Okay, drag force. Okay, now drag force is the resistive force. Okay, it's like friction. Drag is a type of friction. Okay, now since the aircraft has to move in the in the forward direction, so there has to be a force in the forward direction, and this force is called thrust. Okay, this force is called thrust force, and it is acting in the at 90 degrees to the aircraft. Okay, now, and the thrust in the aircraft is obviously provided by the engines. Okay, thrust is provided by the engines of the aircraft, and engines are obviously fitted here. Okay. So the aircraft engines will be here somewhere. You know where fuels are stored in an aircraft? Any idea? Do you guys know?
At the bottom of the aircraft.
Where?
At the bottom, below the area below where the wing is. Like
No.
not
Yeah.
on the wing, but
It is inside the wing. Okay. 70 means 80% of the fuel is inside the wing of the aircraft, and there will be some fuel tank maybe here. Okay, so
there.
that is very less amount. So mostly, let's say 80 to 85% of the fuel is in the wing of the aircraft. Okay, that's why you will also see wings are really large. All right, so yeah, so it's like that. So this is your thrust force, and thrust force always accelerate the body. Accelerates the body. Okay, so that's the property of thrust force. Maybe you may find this statement is not there in the book, but this is always true. Okay, thrust will always accelerate the body. If there is no acceleration, there is no thrust. Okay, thrust may get cancelled out by each other also. Okay, like let's say now just take an example of a cube. Okay, ice cube. Let's take the example of an ice cube. Okay, now you put this ice cube in water. Okay, ice generally floats on water, right? Why ice floats on water? What happens? Why ice floats on water? This is water.
Ice,
Less
ice is-
dense than water.
Ice is?
Less dense than water.
What do you mean by dense?
Uh,
See, ice is
density,
solid,
sir.
right?
Because of the hollow space inside the cube, it floats, sir.
Oh, okay, okay. Ice is okay, and water is what? What is water? Liquid, isn't it? Ice is solid, water is liquid. Usually, you will see that if you put a solid in a liquid, it will sink. It will not float, right? But in the case of ice, this is ice. ice will always float on water because this symbol we call rho, which is density. Okay, this is density, which is rho, which is mass per unit volume. Okay, mass per unit volume is called density. It is pronounced as RHO, rho, RHO. It's a Greek letter. Okay, so this is called your density. That is mass divided by volume. Okay. Yes. Any doubt? So what will be the SI unit of density? Yeah, SI unit of density.
Gram per kg per meter cube.
Who is this?
Vinaya, sir.
Kg per meter cube. Very good. Okay, because mass is kilogram and volume is meter cube, SI unit. So density SI unit is kilogram per meter cube. Okay, so in this case, the density of ice is less as compared to density of water. Okay, that's why ice will always float on water. The ice is not tightly packed. Okay, although it is a solid, but the molecules are little farther away from each other as compared to that of water. That's why ice will always float on water. Okay, now let's take another example. Okay, again, let's say you have a vessel. Okay, and you have some water in it, and you have some solid, let's say some solid ball. Okay, which is like this, maybe some spherical ball. So what you will see, this because of this liquid, let's say water, because of this water, there will be pressure or some force, you can say some force on this ball. Okay, and of course, because of this water, there will be some force on the walls of the container as well, right? And of course, because of the container, there is opposite force with Newton's third law, if you remember. That's how the container is not breaking. If the force due to water, if force due to water is higher as compared to force due to this container, the container will break, right? That's what happens. So some of the aquariums, it will break because the force in the water is more as compared to that of the material that the glass aquarium can resist. Okay. Okay, got it. So this is the force that will be exerted on the ball from all the directions. Okay, got it. Now, how do we calculate this force? So this force can be calculated. Let's say, we'll make another diagram. Just try to understand it here. See, this is a free, suppose this is a beaker, and till this far you have filled some water or some liquid, let's say water here itself. Okay, and the density of this liquid is, let's say, rho. Rho is the density of this liquid. Density of fluid. See, when we write fluid, it can be either liquid or gas. Fluid do not have a fixed size or shape. Okay, so this is some liquid which density is rho. Okay, now if suppose, how do you calculate how much pressure is here, how much pressure is here at these points? What are the pressures? Okay, like when, if suppose this is an ocean. Okay, inside ocean you will be able to swim, let's say on the surface of water you will be able to swim properly, or it's easy to swim on the surface of water. But as you go down, it's really tough to swim, right? It will be tougher for you to swim, isn't it? If you go, if you try to swim at some depth, it will be tough. Why? Because this water is present here. So because of this water, there will be some extra pressure on you, right? That's why it is difficult for you to swim. And even if you try to put, let's say this one is a balloon. Okay. Let's say this one is a balloon filled with air. Okay. Or let's say it's a not balloon. Let's say something. What can we write? Okay. We'll take that example later. Okay. So you understood, no? See, this is position 1 on the surface, and this is position 2. So in position 1, you have only air pressure acting on you, right? Air pressure. Okay, and that air pressure is your atmospheric pressure. Okay. Now, do you know how much this atmosphere put a pressure on you? How much pressure is there because of the atmosphere? Anybody? See, when you are standing in somewhere, let's say you are standing, you are walking, or you are doing some activity. Okay. So there is air everywhere, right? And air pressure will be acting downward because air has molecules and it will be directed towards the center of Earth, right? That force is always there. So air always put pressure in the downward direction on your head. How much pressure is there? So this is called 1 atmosphere, 1 atm. That is equal to 101,325 Pascal. Okay. I haven't told you about Pascals. So let's understand what a Pascal. Okay, I haven't given you definition of pressure also, right? I'm sorry. So pressure, let's write down pressure. Pressure is nothing but force divided by area. That means whatever force you are applying on a particular area. Let's say this is a plate, okay, or a circular plate. And you are applying some force in this F. Okay, and this plate has an area A. Okay, so the pressure on this plate will be equal to F upon A. That's it. Okay. The pressure is always applied in the cross section. Okay, let's say there is a cylinder. Okay, if this is a cylinder, okay, if this is your cylinder, so what do you mean by cross sectional area? Yeah, Ram, what do you mean by cross section area? See, this is axis of the cylinder. And if you cut the cylinder from here, let's say this point, you are cutting your cylinder. So whatever surface that you will get after you cut the cylinder, that is your cross section. And in case of cylinder, it will be a circle. Okay, so we always take the cross sectional area. Maybe let's say you have a cuboid. Okay, if you have a cuboid, and if you cut the cuboid from this plane, on this plane, if you cut the cuboid, if you are cutting the cuboid on this plane, what you will get? You will get a rectangle or a square, right? This is your cross section area. Cross section area. Let me write. Okay. So understood the meaning of cross sectional area? Can anyone please reply? If you guys are not here, I'll just end the class.
Yes, sir.
Yes, sir.
Okay. So you have to reply. You have to keep, if I'm asking some question, you have to reply. Leroshan. Yeah, Mr. Leroshan.
Yes, sir.
So why you are not replying to it? You want some joke, or you haven't trained me for that yet?
No, sir.
know?
Just now I joined, sir.
Just now, why so late? It's already half an hour of class. Anyway.
Sir, my mother then informed me that today I had class.
Okay, it is fine. But did you guys understood the meaning of cross-sectional area? What do you mean by cross-section?
Sir, can you explain it again?
See, that's what I was asking. If you don't know, you have to ask, right? If you haven't understood, you have to ask. See, cross-section, let's, okay. Let me give you another example. Like you all have a pen or a pencil, right? That is what is the shape of your pen? Huh? What
Cylinder,
shape it
cylindrical.
resembles? It's a cylindrical, right? Now suppose you have a pen, right? Let's say like this, something like that. Maybe there is a tip or something. So till this far, it is a cylinder, right? From here to here, let's say it is a cylinder. Now suppose you break or you just sharply, if you cut your pen from here, right? So what you will see on this surface? Now what you will see like this surface will be what? Something like this if you cut from here, right? Isn't it?
Yes, sir.
So what
Yes, sir.
surface is that? What type of surface is that?
Circle.
It's a circle, right? So that is your cross section. Okay, that is called your cross sectional area. Now let's say if you cut from here, what you will see?
Circle.
It will again be a circle, right? So something like that, isn't it? So this is again your circle, right? So that is your cross sectional area. See, if you have like a matchbox or something like that, a box you have, right? If you cut the box from the middle, what you will see?
A rectangle.
A rectangle or a square, it depends, right? What shape your box is made of. So that is your cross sectional area. So this area, when we are writing A, this is your cross sectional area. Okay. The force applied per unit cross sectional area is called pressure. Okay. And pressure must be applied in all directions. Okay. See, suppose at a point, let's say on your head, at this point, what direction pressure is acting? Pressure is acting from all directions. Okay, like this. For wherever it is possible, all direction pressure is acting. So suppose if you have a ball, or if you just take one particle, let's say air molecule. So how pressure is acting? Pressure is acting in all direction in this on this molecule. Okay, so this is how pressure acts. Now tell me, is pressure a vector quantity or a scalar quantity? See, force is a vector quantity. Area again is a vector quantity, right? We have seen this. So is pressure a vector quantity or a scalar quantity?
Vector.
Okay, so force is a scalar quantity. Okay, it's not a vector quantity.
Oh.
Wait, let me write it properly. Just give me a moment, okay? Okay, I'm back. So what I was saying, yeah, scalar and vector quantity, right? So pressure, let's write here, pressure. Pressure is scalar quantity. But you will say, you can ask now, but pressure is acting in this direction, right? In this direction, then why it is not it has got a direction, right? But if you see that this direction is always opposite to this direction is opposite to this direction, so it will ultimately get cancelled. There is no direction of pressure. Okay, it is always directed towards a point. That's why pressure is a scalar quantity, and pressure is equal to, you can write thrust. You can use the symbol T. For thrust you can use T. Okay, T upon A. That's how we calculate pressure. Thrust upon area. Force upon area, because force is also a type of, thrust is also a type of force. Okay. Okay. So before we move further, let's Now, what's the unit? Okay, SI unit. SI unit of pressure. Tell me. So, what is the SI unit of thrust?
Newton.
Newton, because thrust is force, right? So its SI unit will be Newton. Okay, and area, what's this SI unit? Meter square, right? So for pressure, this will be equal to Newton per meter square. That is also called Pascal, and we represent it by PA. Okay, any problem, any part?
No, sir.
Sir.
Yes. Yes, tell me.
No doubt, sir.
No doubt. Okay, so
Yes,
its unit is Pascal, right? PAC. So it's represented by PA. All right. Now, see there. This is SI unit, right? So see, what will be CGS unit? CGS. What do you mean by CGS? Centimeter gram second. So what will be the for thrust? That is force is dyne, right? For area, it will be centimeter square. So pressure will be dyne per centimeter square. Okay. All right.
Yes, sir.
Yes.
Sir, it can be 0.1 Pascal also, right?
0.1 Pascal. Why?
Sir, it is also a CGS unit of pressure, no, sir.
Who said? Where? What did you just say?
No, sir, the CGS unit of pressure is 0.1 Pascal, no, sir.
Okay. See, you are doing conversion. That is not CGS unit. See, Pascal is SI unit. Okay. Pascal is SI unit. You are right now you are doing conversion like 1 dyne per centimeter square. 1 dyne per centimeter square. So this will be equal to, in Pascal, if you will calculate, it will be 0.1 Pascal. How do you calculate that? How you will calculate that? Let's do this calculation. Okay. Since you asked this question, so SI unit, what we know, Newton per meter square, right? Isn't it? Now we know in 1 Newton, you have 10 to the power of 4 dyne. 4 or 5? Huh? Okay, you tell me, in 1 Newton, how many dynes are there? Yes, sir. No one. See, in 1 Newton, you have 10 to the power of 5 dyne. Okay, 10 to the power of 5 dyne. This is also Pascal. Pascal is equal to, see, we are writing 1 Pascal is equal to 1 Newton per meter square, which is equal to 10 to the power of 5 dyne. And in 1 centimeter, sorry, in 1 meter square, how many centimeter square will be there? See, in 1 centimeter, in 1 meter, you have 100 centimeter, right? So 1
The 10 to the power of 4.
Yeah, so 10 to the power of 4 centimeter square, right? So here you can write 10 to the power of 4 centimeter square, isn't it? So 10 to the power of 4, you can cancel out this. So this will be equal to 10 dyne per centimeter square, right? So 1 Pascal is equal to 10 dyne per centimeter square. So if you do the cross multiplication, what we can write? 1 dyne per centimeter square will be equal to 0.1 Pascal. Got it? So there is always conversion is always there, which you can do by yourself if you know the concept, of course. Without knowing the concept, you can't do anything. Or if you try to just memorize it, obviously you will forget one day. Whatever you will try to memorize or just try to mug up, you will forget. Memorizing is not a bad thing, but mugging up is a really, really bad thing. Okay. Your neurons don't remember mugging. It will just for a temporary neurons it will create. It will not create your permanent neurons. Okay, that's how you calculate 1 Pascal into time. So Pascal is this is your CGS. Sorry, this is your CGS system, and this is your SI system. Okay, CGS unit, this is SI unit. That's how you do the conversion. Got it? Okay,
Yes,
let's
sir.
do one problem. Okay, let's do one problem. Okay, wait. Do this problem. Okay, do this problem. Do you want me to read it out? A force of 100 Newton is applied on a nail of cross-sectional area of 10 centimeters square. Find the pressure acting on the nail. Okay.
Sir, is it 10 Pascal?
Don't guess the answer. Find
I'm
out.
not guessing, sir.
How it is 10.
Pressure is equal to force by area applied. That thing only I used, sir.
100 Newton upon what is this?
10 centimeter square.
Dude, you have
Yeah.
to convert this centimeter square into meter square. No.
Oh, yes. Yeah, I forgot, sorry.
Yeah, I know you will be sorry. I knew it. Don't be sorry, man. Don't. Yes, got it. Got it? Anyone? Please tell me the answer. It should not take this long.
Is it 10 pascals?
Who is this? Akankshu? Or
Harshini.
Ishani? Harshini, okay. Harshini. How much are Harshini?
10 pascals.
10 pascals, is it? Let's see. See, let's first
Sir,
understand.
sir,
Yes, sir.
is it 10 to the power of 5 Pascal?
10 to the power of 5 Pascal. Okay, let's see. Okay, whose answer is this? Leroshan?
Sir, Gyanish.
Gyanish. Okay, Gyanish. Okay. So this is Gyanish. Harshini, how much you said?
10
10 Pascal. Anyone else? Okay, let's understand. See, a force of 100 Newton is applied on a nail, right? So the nail will have a cross-sectional area. A nail, let's say the nail is something like that. Maybe some sharp, or we don't know. And you are applying a force, okay? You are applying a force of 100 Newton, maybe using a hammer or something, okay? And the cross-sectional area of this nail is given to you, okay? A, which is equal to 10 centimeters square. Now you have to calculate in SI unit. So first you need to calculate this centimeter square into meter square. So that conversion we need to do. We know that one okay, sorry. So 1 centimeter is equal to 10 to the power of -2 or 1 upon 100 meter. We can write that.
Yes, sir.
Yeah, okay. So 1 centimeter, see, let's say this is 1. Now, if you multiply 1 twice, or let's say 1 centimeter multiplied by 1 centimeter. So can we write 1 upon 100 meter multiplied by 1 upon 100 meter? Is that okay? Please tell me.
Yes, sir.
Okay, we are multiplying equation 1 by itself. Okay, if you already know how to do conversion, that is absolutely brilliant. But for those who are having problem, I'm doing it for them. Okay, so this will be 1 centimeter square, fine, will be equal to 1 upon 10 to the power of 4, you can write, or let's say 10,000 meters square. Now is this clear? So in 1 centimeter square, you can also write this as 10 to the power of -4 meter square, right? Yes.
Yes, sir.
Okay. Now how much was the area? Area is 10 centimeters square, right? So we'll just write, we just multiply by 10 both sides. So 10 centimeters square. Okay, so multiply by 10 both sides. Okay, so what your 10 centimeters square will be equal to 10 to the power of -4 into 10 meters square. Fine. So this will be 10 centimeters square will be equal to 10 to the power of -3 meters square. Fine. Now we have got our area. Now we can find pressure. So pressure is equal to force upon area. Force is 100 Newton and area is 10 to the power of -3 meters square. So this will be equal to 10 to the power of 5 Newton per meter square. Or you can also write P is equal to 10 to the power of 5 Pascal. Got it? Understood?
Yes, sir.
So 10 to the
Yes,
power
sir.
of 5 Pascal is correct. Ganesh, you have got correct answer. Okay.
Yes, sir.
Got it? Okay. Okay, good. See, again, there are some pressures. Let's understand pressure. See, air also puts pressure on all objects, right? Because on Earth, if let's say this is our Earth, right? And this is, let's say, our atmosphere. Let me use this. So let's say this is our atmosphere, okay? Now, see, this atmosphere will always, because air is present everywhere, right? So this all air particles are directed towards where? All air towards the center of Earth. That's what we have studied in gravitation. So if you are standing here, let's say you are standing here with a big head. So air will put pressure on your head, right? And this pressure is called atmospheric pressure. Atmospheric pressure due to air, right? Due to air. And this pressure, the value of this pressure is called, in magnitude, it is written as, let's say, in magnitude, it is 1 atm or 1 atmosphere. Okay. So 1 atmosphere, now in Pascal, 1 atm or atmosphere is equal to 101 3 to 5 Pascal. Okay, or you can write 1.014 into 10 to the power of 5 Pascal. Okay, this is 1 Pascal. There is another unit of pressure. See, these are units of pressure. Units of pressure. So from one unit to another unit, you can convert. So this is ATM or atmosphere. Okay, there is another unit called bar. Okay, so why bar? So 1 bar, I'll just write down, 1 bar is equal to 10 to the power of 5 Pascal. So in previous problem, what we have calculated, this is also equal to 1 bar pressure. Okay, 10 to the power of 5 Pascal is equal to 1 bar. All right. See, there is
Yes, sir.
another unit is mmHg or height of mercury. Okay, that again we will study. mmHg. See, mercury is a metal, right, which is liquid at room temperature. Hg is a metal which is liquid, which is in liquid state. Yeah, anybody is saying something? At room temperature. So what do you mean by, have you ever seen this mercury? Huh?
In
Have you?
thermometers.
Yeah, maybe in thermometer, there is a small amount of mercury, right? So that will fluctuate up and down, isn't it? That's what will tell you the temperature of your body, isn't it? So millimeter of mercury, that means, suppose if you have a tube, okay, and you fill some mercury in this. Okay, let's say you have put some mercury, 1 millimeter, or let's say like that, 1 mm of mercury, Hg, 1 millimeter of mercury. So that will tell you the pressure. This is also one way to measure the pressure of our atmosphere or measurement of pressure. Okay. Yes.
Yes,
Got
sir.
it?
Yes.
Any
Got it,
doubt so far? Okay. So there is again conversion of mmHg. I'm not going into that, but mmHg, let me write complete in front written in sentence. So this is called millimeter of mercury. Okay, these are usually used in a pipe flow. Okay, like like capillary tubes are there. So in that we measure pressure using millimeter of mercury, or in thermometer. Okay, so we use there we use millimeter of mercury. Okay, so 1 mm of, let me write here, 1 mmHg, 1 millimeter of mercury will have a pressure of 133.33 Pascal. Okay, this much pressure of the 1 millimeter of mercury will put this much amount of pressure. Okay, so these are all units of pressure. Understood? Atmosphere, bar, millimeter of mercury. Is this thing clear?
Yes, sir.
See, keep noting it down, okay? Because I don't know if these notes will be there with you guys or not. And most of the things are randomly given in your textbook. Okay, these are very random in your textbook. So that's why I'll request you to keep writing. Okay, you will understand everything in class, I know, but if you won't revise, you will not understand what is this. Okay, what things that we are studying right now. Okay. See, now, because we have seen this example, right? That we have kept something this in a beaker. If you have some water, it will always exert a pressure. Now, what will be the amount of that pressure? Okay, so let's try to find out that amount of pressure. Not this. Why is that? Let's say we have a beaker, something, okay, and you fill some liquid or some fluid, you fill everywhere, means in this beaker. Let's say if completely you have filled this beaker with liquid, some liquid, and the density of this liquid, or better to write fluid, it can be gas also. Density is rho. Okay. Now, what will be the pressure at point 1, at point 2, 3, 4? How do we know this? So let's say we want to calculate the pressure at point 2, at this point 2. So for this point 2, this is the amount of water, or this is the amount of fluid that will be acting on this point 2. Okay, let's say the height of this is h. This height is h, and the cross sectional area is a. Okay, cross sectional area is a. So how do you calculate volume of this hash part? Volume of liquid of height h. So let's call VH. How do you calculate? So this will be area multiplied by the height. That's how you calculate the volume, right? Isn't it?
Yes, sir.
Okay. Now let's say the mass of, okay. Now we know that pressure P2 at point 2 we are calculating, right? At point 2. And let's be clear with it. At point 2 only we are calculating, and we will extrapolate it to point 3, point 4 everywhere. Okay. So point 2, what will be the pressure because of this liquid? So pressure will be is equal to force upon area. That's what we have studied, or thrust upon area. Now force is mass into acceleration due to gravity. Here the force is only what? Weight of this liquid, right? The force is the weight of liquid here, right? Isn't it? Okay, force upon area. Now mass is density. We know that density is equal to mass by volume. Therefore, mass will be equal to density into volume, right? So we can write mass is equal to density into volume into G divided by A. Now again, we know area, volume is equal to A into H. So P2 will be equal to A. So density of the liquid into multiplied by area into height into G upon A. Now A and A will get cancelled out. So pressure at point 2 will be equal to density G and height H. You see? Now you see that pressure, because of this liquid, the liquid that is filled inside this tank, it is only because of the height, right? The height is the only factor that will vary. Rho and G will remain constant. Height, right? So rho, density, and G is always constant. For a particular liquid, right? Understood? But height keeps on varying. Height h keeps changing, isn't it? So at the bottom, let's say at the bottom, what will be the pressure? Let's say the height is capital H. Sorry. Let's say the height is capital H. What will be the pressure at the bottom? So at bottom of the vessel, so what will be the pressure? P, let's say this is 0.5. So P5 will be how much? At this point, pressure will be rho G into capital H. Okay. Understood? Let's say this height is, let's say this height is H4, this 0.4. Okay, H4, let's write H4. So what will be the pressure at height 4? P4 will be equal to how much? Roshan, how much it will be?
One
See, if you-
second, sir.
See, just see this equation. Rho GH, whatever the height.
So
it depends-
density gram H4.
H is the height. See,
That's
you
what
have
sir you
not
asked.
or what? Are you listening to what I'm teaching right now?
Yes, sir.
Yeah. So what is H?
H is the height.
Height of what?
Height of the curve. What is that? The container.
No, height of the filled liquid. So here at this point 2, only this much height, this height of water is acting, right? If you are calculating for height, this capital H, so whole water is acting at this 0.5, right? If you calculate for 0.4, so only this much water is acting at 0.4 liquid. If you calculate at 0.3, so only this much of liquid will be acting at 0.3, right?
Yes.
So this
yes, sir.
H is the height of liquid. H is the
Okay.
height of liquid or fluid filled in the container, or let's say like height of the liquid. That's it. Understood? Yes or no?
Sir. Yes, sir.
If anybody is still having doubt, please tell me. I can explain again. This is important. If you don't know this part, then we will not be able to understand buoyancy. Okay, we won't be able to calculate buoyant force. So pressure at 0.4, at this point, 0.4, what will be the pressure?
Sir, density gram height 4 H4.
Yeah, so gram not, is it G, acceleration due to gravity. G is your acceleration. G is acceleration due to gravity. And we know mostly we'll be taking G is 9.81 meter per second square. Okay. Rho G H4. Understood?
Yes, sir.
So that's how we will calculate. Okay, do one problem. A container. Oh, wait. A liquid of density. Okay, water, that's right. Water is filled in a container of height 10 centimeter, in a container of height 10, or let's write 100 centimeter. Okay. Calculate the pressure due to water at the bottom of the container and at the mid height of the container. Okay, take G is equal to 10 meter per second square and density of water is 1000 kg per meter cube. Find it.
Sir, at full length, the pressure is 10 to the power 4 Pascal, and at half the length, the pressure is 5 to the power 3.
Okay, good. Kind of. Who is this?
Dhyanish, sir.
Ganesh. Very good, Ganesh. So see how you'll proceed for the problem is exactly similar to what we did, right? So first you make the container. See, whenever there is a problem, you always start with that. So it's given that the container is filled with water. Okay. Let's say this, and you have to calculate at the bottom, because of this water, what will be the pressure at bottom. See, read the question properly. It's written only because of this water, right? Pressure due to water. Okay, pressure due to water only we have to calculate. We don't have to calculate any other pressure. So let's say this is 0.1, and at the midway that 0.2. Okay, so midway the height will be how much? 50 centimeter. Centimeter, no? And here it will be 1 meter, or 100 centimeter, right? At the bottom it is 1 meter or 100 centimeter. This is again equal to 0.5 meter, right? And we need to calculate pressure at, let's say, 0.1 will be equal to rho density of water. You can write rho W into G into H1. Okay, so rho W is 1000, G is 10, and H is 1.
1.
So this will be 10 to the power of 4 Pascal. P2
Yes,
will
sir.
be equal to rho W G into H2. That is 1000 into 10 into 0.5. That is equal to 5 into 10 to the power of 3 Pascal. Okay, got it? Correct?
Yes, sir.
Yes,
Or
Yes,
you
sir.
can
Correct,
write,
sir.
or you can also write here 10 kilopascal, and here you can write 5 kilopascal. Now you see, as you go up, the pressure is decreasing, right? As you are going up, the pressure is decreasing, isn't it? Here the pressure at 0.2, pressure is less than at 0.1. So now just imagine this as sea, or some swimming pool. That's why it is always easier to swim at the top, right? Isn't it? And it is always tough to swim in the bottom, right? Because there will be a lot more pressure acting on you as compared to at the top. At the top, only air pressure is there, atmospheric pressure, 1 atm. Now see, this pressure P1 is only because of water. Now if the question says find total pressure at 0.1, and 2, how you will calculate? So total pressure will be equal to pressure at 0.1 plus atmospheric pressure plus 1 atm. Okay, total pressure at this is at 0.1. Total pressure at 0.2 will be pressure at 2, hydrostatic pressure at 2 plus 1 atmosphere, 1 atm. 1 atm is your atmospheric pressure. Okay, and 1 atm we already know how much it is, 101,325 Pascal. Okay, you can just write 1 atm, you don't need to write this value. And don't worry, this question they are not going to ask. I'm just giving you how much is the total pressure acting. Okay, it's not like that if you are on the top there is no pressure acting on you. There is always 1 atm pressure acting always on us. Okay, if you go inside, there will be a lot more pressure. Understood?
Yes,
Anybody
sir.
have doubt
No,
so
sir.
far?
Yes, sir.
And see,
No, sir.
this pressure due to this water or this fluid is called hydrostatic pressure. Hydrostatic pressure. Okay, this pressure is called hydrostatic pressure. So the pressure that we have calculated is called hydrostatic pressure. Okay, understood? So this is what hydrostatic pressure is. Now, I'll just give you five to 10 minutes, not 5 to 10 minutes. I'll just give you 5 minutes to revise everything, okay? Just go through your notes, whatever we have done till now, and then we'll see Archimedes principle. Okay, so hopefully you all have noted what we have done here. Or first we will see buoyancy force. What is buoyancy or upthrust? Okay, just go through your notes, whatever we have done till now. Done. Okay, let's understand buoyancy or upthrust. Okay. Have you ever done the experiment that have you tried to put let's say air balloon in water? Have you ever tried that?
Yes, sir.
What happened?
It floats, sir.
Huh?
It floats on water, sir.
Are you sure?
Yes, sir.
Sir, the
Okay.
balloon will just float away, no, sir.
Okay, see, let's say there is, where have you tried? Have you tried in a sea, ocean? Where have you tried?
In a bucket of water, sir.
Okay, let's say this line represent your this here it is air and here it is water. Okay, and if you just keep that balloon, okay, let's say the balloon, let's make something like this, okay, some thread or whatever you have. If you just keep the balloon, it will be staying there, right? If you fill air, suppose if you have air inside the balloon, it will be here only, okay. But if you put some water and you just leave it, so balloon will partially come inside water, right? But let's take, wait. Okay, first try to we'll come back to this diagram again. Let's say the balloon, if you remember, let's say there is a balloon, okay, and you put any gas other than air, means any gas lighter than air, right? Air is composed of nitrogen and oxygen, mostly 72% or 78% of nitrogen plus 21% of oxygen and 1% of other gases. That means anything that you put is lighter than this. Let's say helium. Usually helium is put filled in this balloons. So if you put helium in this balloon, the balloon will go up, right? The balloon will go up because helium, the density of helium is lesser as compared to density of air. That's why the balloon will go up. Okay. Now, if you fill this balloon with air, so if you fill this balloon with air, so ultimately the balloon will rest on the ground or on the surface of water, let's say, if you have kept it, right? So suppose if you have a birthday balloon or something, if you hang it, it will keep on hanging there itself. It won't, fly away. Why? Because the density of balloon, or the density of air inside the balloon is equal to the density of air, because air is filled inside balloon as well as the outer atmosphere is also air. That's why the balloon will stay there. Okay, got it? But if you put water, let's say instead of air, okay, let's say here it is air, and let's say another balloon. If in some balloon you put, let's say, some water, okay, there is water in this balloon, and there is water. So partially the balloon will come inside water, right? Isn't it? The balloon will come inside water. But if this balloon, if you try to forcefully put inside water, what will happen? You will see there is a force being exerted on this balloon that will try to push away this balloon from the water, right?
The upthrust.
That is your thrust force. Okay. Now see, I hope I'm just trying to give you example here. Now suppose in a sea or any water body, there is a boat. Okay, there is, let's say, boat, and Le Roshan is there in the boat. Okay, he's driving the boat. He's the driver of the boat. Okay, how's that made, Le Roshan? You have any idea? It's kind of heart shape, right? So heart shape it is. All right. So Le Roshan is driving this boat, but the boat is always floating on water. What is the reason behind it? Because
The
yeah,
relative density is less than 1.
okay, what do you mean by relative density? We haven't reached that term yet, but since you said, what do you mean by relative density?
That's what I learned in books, sir.
Okay, that's what you have learned in book. See, relative density is, what is relative motion? If somebody is going this side and again somebody is going this side, their speed will cancel out, right? They to each other, they will be kind of moving. They will be stationary. If it is 10 meter per second, this is also 10 meter per second. So with respect to A, B is stationary. With respect to B, A is also stationary. But if they are going in opposite direction, so with respect to B, the speed of A will be 20 meter per second. And with respect to A, the speed of B will be 20 meter per second. So here we are using relative motion. So similarly, there is a term called relative density. The density of water divided, means density of any object divided by the density of the water. Okay, that is called your relative density or specific gravity. Okay, so there are two terms. We are going to learn about these terms, but not now. Okay. Now see, the boat will always float on this water body, right? Because Le Roshan said of relative density is lesser as compared to that of water. All right. Now what will happen? But there will be always some part of this boat that is inside water. You will see that. Okay. Now there can be few objects. Let's say again there is a water body. Why I am making so many diagrams? Just to make you understand, giving you more examples. There can be some bodies which will be fully submerged, right? If you throw in water, it will go inside water. Okay, let's say some metal. Okay, some metal, it will go inside water. There will be some body which will float partially on water, right? So this is called partially floating, and this is completely inside water. Okay, this one is completely inside and two is partially inside water body or any fluid body. Okay, it doesn't has to be water all the time. Okay, understood? Yeah.
Yes, sir.
Okay, nobody is responding. That's why I also thought maybe everyone slept. I should also sleep. Okay, the weather is really nice, isn't it? Just to go.
Sir, but I am listening, sir.
You are listening? No, that okay. Then I will explain. Okay. Okay. Okay, Liroshan.
Yes, sir.
Now what is that noise? So the density, the fluid will put some pressure on this body. That's what we have studied, hydrostatic pressure. That pressure will be equal to rho density of water, let's say density of the liquid, because let's say this is water. So rho G into H. H is what? This height, right? So that is the pressure by this liquid on this ball. Similarly, on this ball also, there will be pressure by this liquid. Okay. Now, for this ball, this ball is also having a mass, right? So a weight will be acting in the downward direction, right? A weight force of this ball is acting in the downward direction, or you can say gravity, okay, mg. All right. Because this object is having mass, so it will be, there will be a gravitational force acting on this. And there will always be a upward force that is called this force. This is your buoyant force or buoyancy. See, whenever a body is fully or partially submerged in water, there will always be a upward force acting on this body that is called buoyancy, okay, or buoyant force. All right. Understood? Yes,
Sir.
or no?
Yes, sir.
Yes,
If
sir.
anybody is having doubt, so we can clarify it. Okay. So shall
Sir, I
I
have doubts, sir.
You have a doubt? Yes, please tell me.
Sir, is buoyancy and flotation the same?
No, see, because of buoyancy, there will be flotation. Okay, flotation is a property. Buoyancy is a force. Okay.
Sir, is thrust and force like similar?
Wait, who's this? Ganesh.
Yes, sir.
Okay, your voice is not clear. Can you please repeat?
Sir, is thrust and buoyancy similar?
See, thrust, what I said, thrust can be any force which acts perpendicular to the body. Okay. Right now, buoyancy is acting perpendicular to the body. So buoyancy in here, buoyancy is also thrust. Okay. Buoyancy
Yes.
is your upward thrust.
Okay, sir.
Buoyancy, or you can write thrust. Okay. And it is acting in the upward direction. So sometimes it is also called upward thrust. Okay.
Okay,
Upward
sir.
thrust or up thrust. Okay. Now let me write the definition of buoyancy. So can anyone tell me the definition of buoyancy I just said? Can you please repeat?
Sir?
Can you tell me the definition of buoyancy? Anyone?
Upward thrust.
Yeah, upward force exerted on a body when the body is fully or partially submerged, okay, or immersed in a fluid. Okay, so let's write the buoyancy. It's a force. It's an upward force acting or exerted on an object or a body. We can write on a body. See, body, object, particle, all are same. Okay, you'll in different books or different websites, you will find different languages. So don't worry about it. You can write body, object, anything. Okay, just the article will change. Instead of a, you will be using an and like that. Okay, so don't worry about it. When a body or object is wholly or partially, wholly means fully, right? Fully, like this first body, and partially means second body. Half of the body is outside water and half of the body is inside water or fluid. In this case, water is fluid can be water or air, anything. Okay. Partially immersed in a fluid. Okay, that is your buoyancy. All right. So buoyancy is also upward thrust that we have already written. Now, because of this buoyancy, the body will see it. It seems like body will lose some of the weight. Okay. All right. So you can take it. How many of you have done swimming? So when you swim in water, when you go in water, you feel little light, right?
Yes,
It
sir.
is because of buoyancy, because there will be a buoyant force acting on your body because of the fluid pressure. So that is your that is why you'll feel a little lighter. Okay. So on what factors buoyancy will depend? Buoyancy will depend
On relative density. No?
on, okay, number one, the density of the fluid. That this is the fluid. The fluid has density rho, so will depend. Will depend. Already I've written on,
Mass of the object, sir.
yes, the density of fluid. Density of fluid. Number two,
Mass of the object.
mass in, see, mass. Okay, mass, it will depend definitely, mass, or it actually, see, this much amount of volume is submerged, right?
Sir, can we say weight?
So actually it depends upon the volume. Okay, volume of the body. See here, in case one, the complete body is inside, so volume is more. Right here, the only this portion of the body is immersed. That means volume is less. So it will depend upon the volume of the body. Okay, and of course it will depend upon the weight or mass. Not mass exactly, but weight. Okay, weight of the body.
Okay, sir.
Got it? So on these three factors, buoyancy will depend on. Got it? Yes or no?
Yes, sir.
Yes, sir.
So see, what are the applications of buoyancy? I've already given you examples like this boat. How come the boat floats on this water body? Because of buoyancy force. And the relative density, obviously we haven't studied the term. How are fish able to swim properly? Okay, that is all because of buoyancy, right? How is hot air balloon? Why a hot air balloon floats in? Like if you fill air, okay, either you fill air or you fill helium, right? The density should be less. If you fill air and you warm up the air, you heat the air. When you heat the air, what will happen? Usually the air particles are like this, right? If you heat the air, what will happen? The particles will expand, right? So that it will become lighter. It will become lighter than actual air. So density of hot air will be lesser as compared to density of air, right? Because the particles will get expanded. All right, it will occupy more volume. That's how it will be able to float. So these are some of the applications of buoyancy. And next, and swimming. Obviously, why is buoyant force important in swimming? There is a question. Okay, write down few of the questions. I want you to find out the answers. Okay, write down question number 1. In next class, I want these answers. Why is buoyancy or buoyant force? Buoyancy and buoyant force both are same. Okay, force important in swimming. I've already told you the answer, but I want you to find out. Number 2. Okay, types of buoyancy. Find out the types of buoyancy and why it is called so. All right. All right. These 2 questions, can you find out in next class? Can you tell me the answer?
Yes, sir.
Yes, sir.
And yeah, and of course, try to find out some of the examples with explanations. of buoyancy, of course. Buoyancy or buoyant force are same. All right. So I will end the class here. And if you have any doubt in today's class, you can ask me. Okay. And in next class, we will be doing relative density, and a few more terms are there, and we will try to finish this in next class. Okay, Archimedes principle is left. Yeah, and obviously we have done hydrostatic pressure, so principle of hydrometer will be clear to you all. And there are some equations like Bernoulli's equations, Reynolds equations, continuity equations. So those we will see. If it is required, then we'll do, otherwise we'll leave it. These are really easy terms, Bernoulli's theorem and Reynolds number, what is it? So we'll see that, okay? See you. See you next class, bye.
Thank you, sir.
Thank you, sir.
Thank you.
sir.
I'll end the class, okay? Thank you, everyone.
Thank you, sir.